Hello friends, in the previous video we have seen laws of vector addition, that is triangle law and polygon law, and then parallelogram law of vector additions. Today we are going to see what is called resolution of vectors. Okay, now why do we really need it? Okay, in the previous video I had given one example of I started walking towards east through 50 meter, then I walked towards south maybe 50 meter more. Okay, this looks a little small, so I'll just make it big. Okay, so I started from point A, I went to point B and then point C. Okay, so what is my net displacement? Is it not AC? Correct, AC is my net displacement. So what happened is I started from A and I reached C. How did I do that? I went to B and then from B I walked to C. So it's like, just imagine that I am going to walk. Okay, you look at me when I am at point A. Okay, I am standing here. Okay, then you are looking somewhere else. Okay, and in the meantime I started walking. Okay, after some time you saw me and I was here. Okay, so what you thought? You may think that I started from point A and I reached point C, isn't it? So you don't have any reason to imagine that I may have walked to B or then C, or then maybe you can even think that I may have walked from point A to point D here, from point D over here, then over here, then over here, and then over here. You have every reason to think like that. Okay, but then what is the end result? End result is I was at point A initially, but then finally I reached point C. Okay, so this displacement AC, it can be broken down in any number of components, practically infinite number of components. Okay, but what would be the most convenient way of doing it? The most convenient way of doing it is imagining that I walk towards east and then towards south, isn't it? Or then I start from point P here and I'm going to reach point Q here. Okay, so this is my displacement, or maybe this PQ is some vector. Okay, let us call this vector A bar. Okay, and then if I have to make two convenient parts of this vector, what I would do is I would go here and then go here. Correct. So I could say PQ bar would be PR bar plus RQ bar, isn't it? Isn't that convenient? Yes, it is. And that is why we resolve vectors into rectangular components. Now when I say rectangular components, what does it mean? Here this angle is 90 degree. Okay, but then for resolving vectors in these rectangular components, you must have some set of coordinate axes. Okay, so I'll have one x-axis over here, which happens to be the horizontal line, and y-axis, which is the vertical line. Okay, and the angle between x-axis and y-axis is 90 degree, which we all know, and the point of intersection is origin. So always you should have some frame of reference which will include at least two coordinate axes. If you are working in 3 dimensions, then you will also have z axis over there, but for now let us focus on only 2 axes, x axis and y axis. And then I have a vector over here like this, OA bar, let us call it A bar, and I know that Now since a bar is a vector, it has got magnitude which is a, maybe small a, and direction. So for direction I need to specify the angle made with one of the axes. Now let me call this angle as theta. Okay, so now I want to resolve this vector into rectangular component. Now rectangular components means component along x axis and component along y axis. So what I am going to do is, from point O I draw a perpendicular here on x axis. Okay, and from point OA I'll draw a perpendicular here on y axis. Let me call this M and this point as N. Okay, now what we do, we consider this triangle OMA. Okay, triangle OMA. Okay, can you figure out, or can you tell me, suppose A is the magnitude of OA bar. Okay, can you tell me what is the length OM? So for that we have to use little trigonometry. So I'll see what is my cos theta and what is my sin theta. So cos theta is adjacent side upon hypotenuse. So it would be OM upon OA, and sin theta is opposite upon hypotenuse. So it would be AM upon OA. Correct. So my OM is equal to OA into cos theta, and AM is equal to OA into sin theta. Correct. So I can say that yes, this distance, okay, this distance, suppose this point A has got coordinates x comma y, then this distance would be x, and that would be equal to A cos theta, and this distance y would be A sin theta. Correct. So I can say that A cos theta is the x component of my vector OA bar, and A sin theta is the y component of vector OA bar. Correct. So now here my x component is cosine component, because the angle theta is the angle made with the x axis. Now if the angle theta would have been angle made with the y axis, then this sine and cosine things would have got, interchanged. Correct. I'll give you one quick example for this. I'm going to have a force acting at an angle, let us say 30 degrees with the horizontal. Okay, and I want to find the components of this this force along the x axis and along the y axis. Okay, so I say force F is equal to, let us have some magnitude, let us say 80 Newton. Okay, acts at an angle 30 degree with the horizontal, I would say. Okay, I'll call this force F1. Okay, I'll call this force F1. Now I'll draw this F1. Does it look 30 degree? It doesn't, but then it's not a two-scale drawing. So let me have my x-axis here, and this is my F1, and F1 magnitude is 80 Newton, and the angle made with the horizontal theta 1, and I say F1 is equal to 80 Newton, theta 1 is equal to 30 degree. Okay, so my components of F1 along the x-axis and y-axis, so F1 x component is equal to 80 into cos 30 degree, and F1 y component, I would say it is 80 into sine 30 degree. Okay, now this is one, you would think, why is this man doing this? Okay, why is he finding this component? What is the use of this? Okay, but then let us wait, just watch. Maybe I have another vector, okay, which is acting in this direction here, F2, another force F2, and this angle is theta 2. Okay, that angle is theta 2. Okay, so maybe I'll write it here. F2 is equal to, okay, F2, magnitude of F2, how much do you want to take? Shall we take 100? Yes, let us take 100 Newton. And theta 2, let me take 45 degree. This 30 degree, 45 degree, 60 degree, these angles are convenient, isn't it? So I'm taking 45 degree. Okay, so again, F2 x is equal to 100 cos 45 degree, and F2 y is equal to 100 sine 45 degree. Okay, now you must have seen here, this F1x, okay, it acts in this direction, okay, and F1y, it acts in the vertical direction. So let us have our y axis here. Okay, this is my y axis and this is my x axis. Okay, now F1x, F1y, F2x and F2y. You know what? I want to find the resultant of F1 and F2. Okay, so over here I see that along the x direction F1x is acting and F2x is also acting along the x direction. Similarly, F1y and F2y, they are acting along the y direction. So can we add them? Yes. So I can say total force in the y direction. So sigma Fy is equal to F1y plus F2y, and total force along x direction sigma Fx is equal to F1x plus F2x. Okay, so what? Now I have these values, 80 cos 30, 100 cos 45. You have calculators, you can calculate, you just add them. Okay, and you add this F1x plus F2x. Okay, and then what would you do? What would you do? Now you add them and then you get the total total force in y direction and total force in x direction, and you can get the resultant. You can use Pythagoras, or rather parallelogram law of vector addition. In this case, the angle between fx and fy, is it not 90 degrees? So anyway, that cos 90, r is equal to root over p square plus q square plus 2 pq cos theta, the derivation which we did in the last video. Okay, so angle theta is 90 degree and cos of 90 is 0, isn't it? So my resultant would be square root of sum of squares of the component forces. So my resultant would be equal to root over sigma fx square plus sigma fy square. So now here, what did I do? I didn't try to find the angle between the two forces, okay, or angle between the two vectors. What I did is I just resolved them along the x-axis and along y-axis. I added the total force along the x direction, I added the total force along the y direction. I just took the resultant of them. Okay, so I didn't even have to find out what is the angle between these two. Okay, it can be done that way, but then there are different ways of addressing problems, and resolving forces is one of them. Okay, resolving forces can be helpful to a very great extent. Okay, so that is the logic behind resolving forces, right? So that was about vectors and scalars. We are going to be discussing the vector product and scalar product of two vectors, but then that would be in later classes. Thank you so much.